We learned in our last video, and when we solved the following problem. Part 8 of this homework problem was we found an interval on x such that the approximation error, or what's this? This is the original function minus the approximation, is less than 0.002. And we found that two different ways. You'll see here in the blue line, we plotted this thing in our calculator, and our calculator showed us that as long as x was between 1.066 and minus 1.066, the error was less than that amount. That was the true error. Then the second way, we used the remainder theorem as demonstrated here in green, where we found an upper bound to the error, and we found that the interval was a little smaller. You'll see I put the notches green inside the red such that the interval was a little smaller. And that made sense because we were using approximation to the error. Now remember, these approximations to Taylor series, this is not some boring little math problem. Approximations are what make products cost effective. That's what breakthroughs in being able to simplify and reduce cost make consumer products viable. So when you work these problems, think you're getting that electric battery cheap enough to be mass produced. Anyway, we're going to look at part B now of this problem. So I'm going to look at part B. We've got a new question here. Here we want to find the order n. Remember what n is. How many terms do I need in that polynomial such that the error in x is less than 0.001? And we're given it on this interval. So the customer might have said, I need your approximation. Or maybe TI told you in their calculator, I need to have a cosine approximation this good. And you're trying to do some analysis to figure out how many terms do I need? How many terms do I need? So remember what we're looking at again. Let's write down that cosine approximation. So we got the cosine of x, and it's what? It's 1 minus x squared over 2 factorial plus x to the 4th. And 4 never comes out very well. 4 factorial minus x to the 6th over 6 factorial. How many terms am I going to need? Am I going to need the 6th? Do I need to go yet another one? Do I need to go to the 8th term? How many do I need? Dot, dot, dot. Where am I going to stop? Where am I going to truncate this? Well, you could, the first way you could do it is put it in your calculator, right? You could, remember, where's the error going to occur? Where's the error going to be greatest at? We already said the error term, which is going to be this, minus the approximation, which could be that right here. That's going to be an even term. The error is going to be maximum at these endpoints, pi over 2. So you could just plug in pi over 2 into that error term and see how many terms you would need. And you keep trying. Go to the 6th term, go to the 8th term. We want to be a little more, and actually in this case, the remainder theorem could get you an answer much quicker. So let's look at this remainder theorem right now. Remember, that's kind of a complicated beast we're trying to understand. Now, the remainder theorem is going to say the following. It's going to say let's go back to black. It's going to say the remainder after n terms is going to be equal to the derivative, the next derivative. Now, in this case, since all the terms are even, if I stop at the nth term, which is the second, it's 2n term, the next term is going to be 2n plus 2. See if you get that. So if I put in 3, if my last term is the 6th term and n's equal to 3, my next derivative is going to be 6 plus 2, or 8. Okay, I need to evaluate that at this magical c at x to the 2n plus 2 over 2n plus 2 factorial. All right, that's the true error. That's the true error, and I want that to be less than 0.001. Okay, what's c again? Well, c, that magical c, we don't know what it is, but we know it's on this interval between the center point 0 and the value at x where we want the error. Because remember what that is. We can also call that the error. Okay. Now, we're going to say the following. If you remember from the last problem, we're going to use the absolute value. We would say that's equal to the absolute value of the error of x. And that would be equal to, it's going to be less than or equal to, remember this term here. From our little work we did before, we said this is going to be either kind of the cosine of c or the sine of c. Okay, depending on, it just flips back and forth. And we're going to maximize that. How are we going to maximize the cosine of c on this interval from 0 c? And what does x go to? Oh, look, x goes to pi over 2. So I could put pi over 2 here. So what's going to be my maximum of the cosine of the sine on that interval? Well, it's going to be 1. Okay, so this term right here is always going to be less than 1. So I go from an equal sign to being less than 1 times x to the 2n plus 2 over 2n plus 2 factorial. Okay. Okay, what do I want that to be? Less than 0.001. I'm going to change colors just to make this a little more fun. What's x? What's x? Well, remember, where's the error going to be the maximum? Is it going to be the maximum at the center point? Is it going to be maximum at the center point here? No, the error is going to be the maximum right here at the edge, pi over 2. So I'm going to go back and I'm going to say this is the error at pi over 2. Pi over 2 going to be less than pi over 2 times 2n plus 2 over 2n plus 2 factorial is less than 0.001. Okay, well, how do I solve this? What am I trying to find? I'm trying to find n. And there's no magical way to reduce that. You just try different n's. And you say, you put in n equal 2. N equal 2. I don't have my calculator here, and I just know what the answer is. N equal 2, you're going to get a number. I'm going to guess here. At n equal 2, this thing right here, which maybe I'll call this g function of n. When I put in 2, I'm going to guess that that's 0.003 or something like that, okay? It's not good enough. When I put in n equal to 2, n equal to 3, sorry. If I try n equal to 3, n equal to 3, I find out, sure enough, this term right here, what term am I talking about? This term, if I put n equal to 3, I'm going to get pi over 2 to the 8th power over 8 factorial. That's going to be less than 0.001. Sorry. So what have I just found out? If I do that, the error term is less than this term, is less than that. So the error at pi over 2 is going to be less than 0.01 when n equals 3. N equals 3. What does that mean? Notice the next skip term up here is n equals 3. 6 plus 2 is 8. So the last term is the 6th order one. Let me just write that down here. Okay, so what we need to satisfy our problem here and to solve TI's problem, we need a 6th order approximation. That's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. With this we can say that the cosine of x minus p6 of x is going to be less than 0.001 on x less than pi over 2. Okay? Now when you go to your calculator, you can then verify that. And okay, I got my trusty calculator out to find these values here. And what I found out at here pi over 2, the error, or the absolute value of the error at the value pi over 2 is equal to 8.94 times 10 to the negative 4. So you see, with our remainder theorem approximation, we're able to find the correct order. We need a 6th order in order to get this error to be less than that. And sure enough, the true error, which I can find with my calculator, is less than that. It's less than the requirement here. Remember, the requirement was y equal 0.0001. The true error is less than that. And again, on both sides. Okay, so the remainder theorem in that case, if you're finding a large order one, we had to have a very tight error. It could have been a very convenient way to see how large a polynomial we would need. So again, next we will talk about, we'll have a series on how the TI calculator actually computes the cosine of x using Taylor series. See you soon.